Welcome to Brain Vision.
In this example, we're given two identical containers of gas, except the gas inside is different. So one of them has argon gas in it, and one of them has krypton gas in it. Now we're told that the masses of each gas inside these containers is the same, and that the pressures are also the same. And we also know, since they're in the exact same container, that the volumes are also the same. So what we're going to try to do is find the ratio of the average kinetic energy per molecule of the krypton gas over the argon gas. So first things first, we're going to need some sort of expression that relates quantities like pressure and volume to the amount of gas we have, and also to the average kinetic energy per molecule. And really, that equation is just a version of the ideal gas law, and it is P equals 2/3 big N over V times the average kinetic energy per molecule. And what we want to do here is solve this equation for the average kinetic energy per molecule. And then we'll plug in all our values for argon and krypton and take the ratio of the kinetic energies. So we'll want to multiply both sides of this equation by 3V over 2N, just to move all this stuff to the other side. And if we do that, we'll have 3PV over twice N. Okay. So now let's see what this ratio would look like. If we took the ratio of the average kinetic energy per molecule of krypton is up top over argon, in the numerator we would have 3PV over twice N, where let's see what's going to actually be unique here. We know the pressure is the same for both, so we don't need a subscript to that. We know the volume is going to be the same for both, so the same thing goes there. Though we don't know anything about the number of molecules, so we'll put a subscript on that. And similarly, the denominator is going to be exactly the same, except with a N sub argon. All right. So we can see a bunch of stuff's going to cancel out, right? 3PV, 3PV, 2 and 2. And then we'll be left with a 1 over N sub krypton and a 1 over N sub argon. Or, if we simplify that, we will have the number of argon molecules over the number of krypton molecules. Okay. So this is looking pretty good. However, we actually don't know what the number of argon molecules is, or krypton molecules, right? We have the masses of the gases. So we're going to have to go between number of molecules and masses somehow. So the way to do this is going to be to remember, one, how to convert from a number of molecules to moles. And the relationship for that is big N over Avogadro's number is equal to the number of moles. And then once you have the number of moles, you can go to mass with this relationship, which is that the mass of a substance is equal to the number of moles times the molar mass of that substance. So if we were to substitute this equation in here for little n in this equation, we would have little m equals big N, big M over Avogadro's number. And if we were to solve this for big N, we would have N equals mNA over big M. And that's just if I had multiplied both sides by Avogadro's number over the molar mass. Okay, So here's how you go between the number of molecules and the mass, little m, right there. So I could substitute this into my ratio over here, and let's see what happens. So big N for argon over big N for krypton is going to be equal to little m for argon times Avogadro's number over big M for argon divided by little m for krypton times Avogadro's number over big M for krypton. So we can see that Avogadro's number will cancel out because that's just a constant. And also, the masses, little m of argon and little m of krypton, are assumed to be the same. So we can cancel those out. And again, we're just going to be left with a ratio of molar masses now instead of a ratio of number of molecules, which is going to be 1 over the molar mass of argon divided by 1 over the molar mass of krypton, which is just the molar mass of krypton over the molar mass of argon. All right, so now these are just both values we can look up in our textbook or online. And the values I will be using is 83.798 grams per mole. And the units don't really matter on these as long as they're in the same units, since we're taking a ratio. And the molar mass of argon will be 39.948 grams per mole again. So units cancel out, and we're just left with 2.1. So the ratio of the average energy per molecule is just equal to the ratio of the molar masses. And this happens to be 2.1, which makes sense because krypton is about twice as big as argon, or its molar mass is about twice as much. So there you have it. We just calculated the ratio of the average kinetic energy per molecule for krypton and argon gas, given that the masses, pressures, and volumes of the gas were all the same.